Welcome. This is Geometry B, Unit 9, Lesson 3. We're talking about probability, and this lesson is simple probability. Now, it says simple. It may not come across as being exactly simple. Remember, this is a new concept for many of you, and so have patience, listen carefully, and take detailed notes. On the left is a list of the things we need to hit during this video, because these are the concepts talked about in this particular lesson. And so we're going to define probability. Probability. What is probability? The definition of probability, I'm going to word it a little differently than the lesson, is the number of ways to win, or the wins, divided by the total. The wins divided by the total. The number of ways to win. Let me give you an example. Let's say we have an experiment like flipping a coin. The sample space for flipping a coin is a head or a tail. And if it's a fair coin, then we can assume that the probability of heads and tails are equal. It's not a weighted coin or anything like that. So let's say we want to calculate something called the theoretical probability of getting a head when flipping a coin. We would note that P of H, the probability of getting a head. And so we look at the sample space and we say, how many ways can we get a head? There's just one. There's one head listed in the sample space. Divided by the total number of outcomes. The total number of outcomes from flipping a coin are 2. So note that is 1/2, which is 0.5, which is 50%. You need to be able to express a probability as a fraction, as a decimal, or as a percent, and interchange between those three forms, knowing that they're equivalent. Now, I mentioned that this is theoretical probability. This is what should happen. But there is a difference between a theoretical probability and experimental probability. Experimental probability says I actually take a coin and I start flipping it. And I flip a coin 100 times. And out of those 100 times, I get heads 63 times. 63 heads. Then the experimental probability of getting a head is 63 out of 100, or 0.63, or 63%. Do note that that's not the 50% we got before. That's actually greater. We got a higher number than we expected. Okay? And that is actually not unusual. But there's this principle called the principle of large numbers. Which says this: if I do more experiments, I expect theoretical to be closer to experimental probability. Closer to experimental. Okay? So let's say I conducted this experiment by flipping the coin 1,000 times rather than just 100. I would expect to get a closer answer to 50% than I did with flipping it 100 times. Okay? So the more you conduct an experiment, the more likely you are to get close to, or exactly on, but usually just close to, the theoretical probability. Theoretical probability is the expected probability, the expected outcome. Experimental is what actually happens when you conduct an experiment. All right, so we've talked about flipping a coin, experimental versus theoretical. let's go ahead and go to all the other cases. What about rolling a die or drawing a card or all of these other experiments we can conduct? If I roll a die, the sample space for rolling a die, the sample space is 1, 2, 3, 4, 5, and 6. Okay? Because that's a 6-sided die. It's a 6-sided cube. Okay? So let's say, what is the probability of getting a 3? Well, how many 3s are there in the sample space? There are 3 of them. There's 1 of them. Sorry, 3 of them. 1 of them, don't let the value become the number. There's 1 3, and there are 6 possible outcomes. So the probability of getting a 3 is 1/6, or 1 out of 6. And I'm not going to take the time to do the arithmetic to figure out the decimal and percent values. Okay? That's rolling a die. Drawing a card. If we use a standard playing deck, what is the probability of getting a spade? Probability of getting a spade. Well, there are in a standard playing deck 13 spades, and there are 52 cards. So 13 out of 52 reduces to 1 out of 4, or 0.25, or 25%. So the theoretical probability of drawing a spade when drawing a card at random from a deck is 25%, or 1/4, or 0.25. What about drawing a marble? Okay, I'm going to go to a new slide here. Oh, I'm drawing a marble. I didn't create a new layer, so let me do that here. Okay, something's acting up here. There we go. Okay, so I want to draw a marble. So I'm going to put some marbles in a bag. Let's say there are 12 yellow marbles, and there are 6 green marbles, and there are 2 red marbles, okay, in a bag. And I put them in a bag and I shake it up. And I blindfold somebody and have them reach into the bag and draw 1 marble out of the bag. What is the probability of getting a red marble? The probability of getting a red marble is the number of red marbles in the bag, 2, divided by the total number of marbles in the bag. 12 plus 6 is 18, plus 2 is 20. So there are 20 marbles in the bag. So the probability is 1 in 10, or 0.1, or 10%. Okay? And so that's drawing a marble. So we've talked about these things so far. Now I want to get to what's called a compound event. Compound event is more than one event. Okay? And there's something called the multiplication principle. It says basically you multiply compound probabilities. So the probability of getting a red times the probability of getting a green is the probability of getting a red and a green when drawing from a bag of marbles. Now there are 2 ways we can draw from a bag of marbles. We can draw with replacement. That means I'm going to draw from the bag, look at the marble, put it back in the bag, shake up the bag, and draw again. And so in this case, the number of marbles in the bag doesn't change because I put the marble back. We can also draw without replacement. That means That means I'm going to draw from the bag, look at the marble, not put it back, keep it in my hand or set it aside, and then I'm going to draw again from the marble, from the bag. In this case, the marbles in the bag have changed. The population of marbles in the bag is different. When we draw with replacement, we say the events are independent. That is because the outcome of the first draw doesn't affect the outcome of the second draw. The population of the bag has not changed. When we draw without replacement, the probabilities are dependent. Okay? And so here we go. The probability of, let's say, a red and a green. Probability of red and green is the probability of drawing a red times the probability of drawing a green. Okay, because I put the marble back with replacement, the probability of green is not any different than it would have been had I drawn a blue or a yellow or anything else. Okay, so the probability of drawing a red is 2 out of 20. The probability of drawing a green is 6 out of 20. And 2 times 6 is 12 out of 400. Divide by 4, we get 3 out of 100, or 0.03, or 3%. Okay? So we use the multiplication principle to find a compound probability, multiply the probabilities of the two events, and get a combined outcome. Now, without replacement, the probabilities are not independent. So the probability of red and then a green becomes the probability of a red times the probability of getting a green given, that's what this bar means, given that I drew a red. Okay? So the probability of a red is 2 out of 20. But now the number of reds has decreased by 1, and the total marbles in the bag has dropped to 19, not 20. So the probability of drawing a green is now 6. There are 6 greens left in the bag out of 19. And 2 times 6 is 12. 20 times 19 is 380. And reduced by 2, 6 out of 150 and 40 is 190. Reduced by 2 again, 3 out of 50 and 45, 95. Okay, and I'm not going to take the time to figure out what that is as a decimal and a percent. Okay, so without replacement, dependent. With replacement, independent. Without replacement, you've got to consider the new population that you're drawing from when calculating the probability. That's really the breakdown.